Hello, everyone, and welcome to the Advaith Vutukuru Show. Today, I'm honored to be joined by Dave Schlossberg, a leader in public service and energy policy. Dave has been a strong advocate for clean energy, sustainability, and responsible economic development. Throughout his career, he has worked on important issues, including environmental protection, renewable energy, and creating more sustainable policies that help communities transition toward a more sustainable future. Today, we will be talking about the future of energy, including exciting developments like nuclear fusion and how they could shape the world for the next generation. Hello, Mr. Dave.
Hello, thank you for having me. I'm pleased to be here.
Thank you for being here. Is there any comments that you'd like to state before we start the interview?
Sure. My research and experience is mostly with fusion energy. So trying to understand how we can make that work, what the benefits are, how we can quantify that, and how we can both understand it from a science point of view, as well as try to use it to power clean energy and turn it into electricity.
For the students or people in the world that might not know what fusion energy is, can you explain to us what fusion energy is?
Sure. Yeah, I'd love to. Fusion is a process that happens when you have two light elements, two nuclei or two atoms with no electrons. And those two nuclei um, have so much energy they can overcome their natural repulsion, and they come together and they fuse into a single product or a single atom, and they generate energy when they do that. And you may say, well, where does that energy come from, Dave? And the energy comes from an equation that you probably have heard of, and a lot of your viewers have probably heard of, that relates energy and mass, right? So there's an equation E equals mc squared.
O E equals squared. Okay.
Yeah. So the way fusion works is um, when those two nuclei come together, there's
Yeah.
a little bit of mass difference between the initial reactants and the products. And that little bit of mass difference gets multiplied by c, or the speed of light, squared. And so it produces substantial energy. And so that's the basics of fusion, nuclear fusion. And you may say, well, how do we actually do that, right? How do we do that on Earth? Because there's a couple different fusion reactors.
Yeah.
Um, you probably have seen one of the fusion reactors today. So has your so has your audience.
Yeah.
Um, One of the fusion reactors is the sun, right? So stars are giant fusion reactors. And the way they work is by confining this hot gas through their gravity. But we can't do that on Earth because stars are so huge they wouldn't fit. So, right? So we've developed a couple different ways to confine this hot gas or plasma long enough that it'll fuse together. And um, and so that's kind of an introduction to fusion. And I can say more about it if you like, or we can talk about other topics.
So like the nuclei or the nucleus of each atom like combines to become like a bigger. That's correct.
Yes, exactly. So in our case, we use hydrogen.
Yeah.
So specifically two isotopes of hydrogen.
So
And
it yeah.
go ahead.
So it's like a different type of like energy type of thing, like you know, it can like power houses and stuff.
Yeah, right. So what happens is when the two nuclei fuse together,
Yeah.
they produce a particle that has a lot of energy.
Hmm.
And that particle can deposit that energy into a material and heat it up. And so we can use that heat to create electricity. So that's the
Oh,
way a power plant would work, is you'd make fusion happen kind of in the center of your big chamber, and then the products would heat up the walls, and the walls, you would use that to make steam and steam to turn a turbine. That's
I
how you make electricity from it.
wow. I find it so fascinating that like on Earth, the sun's energy is being recreated. Like I don't know why. That feels so fascinating, right?
Yep.
So, in the past, I've seen things like, they used to run trains off coal, but then it slowly switched on to like diesel and gas and then electric, like wind power. solar power, and all that, right? So all that's still good. Do you think that like fusion energy would be able to run like day-to-day things like cars or trains?
That's a great question. So right now, a lot of the fusion reactors and the fusion energy sources that we think could work are really big.
Yeah,
So they're like the size of like a nuclear power plant now,
yeah,
mostly because it's hard to keep this hot gas where the fusion happens. It needs to stay hot long enough for the fusion to happen. And by hot, I mean like 100 million degrees Celsius.
hundred.
So temperature of the sun hot, right? So if you can imagine having that in your car, there wouldn't be a lot of ways to keep it hot. It would kind of leak out and heat things up. So if you have a big chamber, then you can keep things in the center and keep it relatively hot. But there are designs and ideas both in the public slash academia and also in private fusion
Yeah,
to make a reactor that would maybe fit on the back of a tractor trailer truck.
yeah.
But that's probably the size scale, the smallest size scale that people have thought of.
Wow.
Starting it up and turning it off, but I think it works better mostly when it's just steady state and you just kind of keep it going like you do um, like a power plant now.
Okay, that makes sense. Yeah.
Yeah,
With renewable energy, how do you see fu nuclear fusion energy working alongside with renewable energy?
that's a great question. Yeah, um, I think all sorts of alternative energy and renewable energy are great. You know, all options on the table. Um, Something that makes fusion different than some of the renewable energies is what's called its energy density. So if you think about it, um, for fusion and a nuclear power plant, you can get a lot of energy out of like a small footprint, right? So you can have a power plant that's, I don't know, um, the size of a couple houses, but that power plant powers a New York City or San Francisco.
Yeah.
Um, Renewable energies like wind power and solar power, you need huge amounts of area to get that kind of power generation. So they're kind of complementary. Nuclear power, fusion energy, can provide what's called a base load.
Mm.
So it can provide um, energy that is needed all the time. You kind of keep it on, you turn it on, it's pretty efficient in size. And then as the sun comes out or as the wind blows, you can add on to that with renewable energy. So one way that fusion energy and renewables can work together is to have fusion be more of a base load and renewables be more of the fluctuating supply.
So, do you think nuclear fusion energy can address climate change and global warming?
That's the plan. That's exactly the plan. So there's a big push right now, both in the US and all across the world, to try and develop fusion energy so that we can help reduce help reduce emissions and help with the climate change issues. Um, the byproducts of fusion um, really aren't that detrimental.
Yeah.
So the kind of fusion that we do now, you get a helium atom out. So just like the helium you have at parties where your voice kind of squeaks when you eat it or whatever, right? So it's pretty benign. It's not very damaging, the byproducts. And so in that sense, it's a very clean energy source. Um, One of the downsides is that the facility, like the infrastructure will become radioactive at the end of its lifetime in 30 years or 40 years. But while it's producing energy, there's isn't really any detrimental byproducts. So certainly fusion energy can help in terms of being a clean energy source. It's also very efficient.
Yeah, of
Um,
course.
in terms of like energy efficiency, um, you could get a certain amount of energy from a big truckload of coal, sorry, a train car of coal.
Yeah.
You'd get the same amount of energy
Yeah.
from a pickup truck of fission fuel, and
Oh,
then you get the same amount of energy from a water bottle of fusion fuel. right? So you
Whoa.
get a water bottle's worth of energy compared to a train load of coal. So it's very efficient.
So, the one flaw is that at the end of its lifetime, it becomes radioactive. So, would you say that you guys are working on like fixing that flaw, or
There's definitely there's definitely research ongoing to say how do we address those radioactivity issues at the end of lifetime, as well as um, some of the fuels that we use for fusion will have different products that may not activate the housing as much, and so that's also research that's ongoing.
so what? Like, I mean, the way you explained it, you made it seem super simple, but like, which challenges would you say like you guys like experienced while trying to like find the exact way of building nuclear fusion energy?
That's a great question. So, in general, the one of the main challenges in fusion energy is that you're dealing with some material that wants to expand. So it's so hot. If you think about like if you had a balloon and you heated it up,
Mm.
what's going to happen to the balloon?
It's gonna pop.
Yeah, right. And so what we want to do is if we have a balloon full of hot gas or plasma that we call it, we
Yeah.
want to confine that gas. And so one of the big challenges of fusion is how do we confine that gas either with magnetic fields or with very dense material that we use to compress it spherically. And it's taken us a while to try to figure out how to do that. There's been research going on for probably 60
Oh,
years.
60. Wow.
Right. And one metric that people use to judge success is to say, well, if you want to build a power plant, you want it to make more energy than it uses,
Yeah.
right? That's pretty
Yeah.
straightforward.
Yeah.
So, how much energy are you producing? And up until 2022, no one had produced more energy than they used to start the reaction. But at the National Ignition Facility at Lawrence Livermore National Lab, on December 5th, we were the first people on Earth to achieve a fusion reaction that produced more energy than was used to start that reaction. So that was a really big milestone for the whole world, the whole community. Um, and it was based on that 60 years of research. We didn't do it all ourselves for sure. But that was a marker to say, hey, we've started to really get to the point where we've addressed and have tackled those challenges.
That that's fascinating. That like out of everyone else, it was like the first batch. And it's 60 years worth of research, you said?
So it was, yeah, it was the first time that we got more energy out than we used to start the reaction. We had tried many times, so it wasn't necessarily the first time we tried it, it worked. Um, but it was the first time that anyone has demonstrated that you can get more energy out in a controlled laboratory setting.
Wow. Okay, so do you think that the nuclear fusion energy could like replace non-renewable energy like fossil fuels and stuff in the future? I mean, you did say that a water bottle full of nuclear energy is worth as much as a trainload full of coal, but like would you say that it's 100% more effective and way more efficient, like way more efficient than every single one of the non-renewable energies?
It's definitely more efficient than the non-renewable energies. It's also, although harder to do,
Mm.
so people are pretty good at burning coal. Um, and so in that sense, there's some inertia to say let's keep with what we know how to do. But yeah, I think once we understand and can demonstrate fusion power as a commercial enterprise, I think it can replace non-renewables for sure.
Yeah.
Um, I was just going to say that also there are some private fusion companies, not associated with the lab, of course, but private fusion companies that are looking into building fusion power plants where there used to be old coal power plants.
Also replace
Yeah. Yep. So they're taking out the old one and saying, let's drop in a fusion power plant and use the existing infrastructure to try and deliver energy to the grid.
So as fusion energy becomes more, popular and more people start to use it and it becomes more affordable, how do you think it will affect the economy?
So it's a great question. So ideally, fusion would be developed in a way that would provide energy to all different levels of civilizations with different economic resources, right? So yes, we could develop it in the US, say, and that would help boost the economy. But ideally, we'd want to deploy this kind of all across the world to countries that may not have power infrastructure, energy infrastructure right now. The nice thing about fusion energy is that there isn't really a risk of proliferation of nuclear weapons like there is with fission power plants. So that kind of removes that concern. Um, and so, in terms of improving or affecting the economy, ideally, fusion energy would be accessible to many, many people. And estimates have said it's probably in the um, tens to hundreds of trillions of dollars, kind of a industry.
Well,
If when it takes off, because it's involved in energy, it could be a very big economic market.
wow. So, how long would you say until like cities and other, you said other countries, right? So how long would you say until cities and its other countries start to, be powered by fusion energy?
So that's a good question. It's always hard to predict the future. Um, I, I think there's been tremendous progress recently, both at Lawrence Livermore National Laboratory and other institutions. Um, I'm enthused that private industry is getting involved. A lot of times um, when research transitions from public institutions and then private industry gets involved, there's an acceleration because of money and effort. Um, and so, I mean, I'm hopeful that we would see a fusion power plant in the next decade or two.
Wow.
Um, so in your lifetime, I would say there's going to be a fusion power plant.
Okay, wow. Looking forward to that. So, when I did my research, I saw that Lawrence Livermore Lab is like kind of helped and kind of funded by the government. So how would you say the government has helped in like being how would you say the government affected the progress of the fusion energy?
Yeah, that's a great question. So Lawrence Livermore National Lab is funded by the National Nuclear Security Administration, or the NNSA,
Yeah.
and um, those resources were essentially what helped build the National Ignition Facility, which is what has produced these first of a kind results. So the government has invested in the National Ignition Facility because there's a fair amount of its research that focuses on what's called stockpile stewardship. So the nation has a stockpile of nuclear weapons, and heaven forbid we ever have to use them. But since the 1990s, we are not able to test them. And so it's kind of like you have a car
Yeah.
that's 40 years old and you can't turn it on, but when you need to turn it on, you want it to start every time, all the time, no questions asked,
Yeah.
right? So how do you do that? Well, the government has provided resources to say, let's build a facility that can test some of the physics
Sure.
of those systems at small scale to try to understand it and buy down the risk on the stockpile. And so the government has invested in this type of fusion, which is called inertial confinement fusion. Um, and they've really provided the mechanism and the vehicle for developing um, these successful results. So it's really mutually beneficial for
Yeah.
both the government investment and then also a spin-off, which isn't directly related to the NNSA, is some of the fusion energy applications.
Okay. So
It's a good question. So here at Lawrence Livermore National Lab, we're not building a fusion energy power plant.
yeah.
The National Ignition Facility isn't designed to produce net energy. It never was.
Yeah.
It was more designed to be a test reactor to demonstrate that we can get ignition. And so the government's investment isn't necessarily that we're going to build a power plant and then we give money to them once the power plant comes into effect. It's more that they're providing the resources to develop the underlying physics and knowledge. And then there's actually a really nice collaboration at the lab with private industry through the inertial fusion energy in the Institute for Inertial Fusion Energy. And the way that works is that we work with private companies who are building those fusion power plants. So I think does that answer your question about how that works
Yeah,
kind of with the
the
government or?
LLNL is basically just like where you like, kind of like understand and research about like how to make it, and then the power plants are where you like mass produce it and then like, put it into real action.
Yeah, there's certainly applications that NIF is working on that is uniquely suited to NIF, right? So the mission of the National Ignition Facility, or NIF, is there's three missions. One we talked about is stockpile stewardship, and it's kind of the only place you could do that. Right now, there isn't really, even in a fusion energy power plant, it'd be difficult to do the experiments that we do here. One is ignition and inertial chemical fusion, and the other one, which is really interesting, actually, is called discovery science. And so one of the things we do on the National Ignition Facility is we probe um, states of matter that you can't get anywhere else in the universe. So say you want to understand how the interior of Jupiter looks or works with massive pressures compressing the core there. We
Yeah.
can simulate, or we can actually demonstrate those pressures on NIF, and we can understand how shock waves propagate out from a supernova. So, so I don't know if I'd say the power plant's where the action is, but there's action at NIF too, I guess is my point.
Okay, so the final question I'd like to ask you is there any like advice that you'd like to give students like me or people who aspire to be like you one day?
Sure. Yeah, I would say follow your curiosity. And as much as you can, don't be intimidated by thinking something is too hard or too complicated or too professional. Um, a lot of this research and a lot of this this discovery is just by people being curious and saying, "Hey, I wonder if what would happen if we did this kind of experiment." And the lab is a great place to get involved. So there's um, different programs that we have. There's a fantastic student internship program run every summer that you can go to the website and apply on if you want to be involved. It's usually for college and above, although I think there is also a high school um, program through the Discovery Center. The other thing to get involved that you could do to get involved is there's tons of information on the web, and so you can find some of that on fusion and fusion energy, and just start to follow your curiosity.
Yeah, I'll sure be checking out that program though. So thank you so much, Mr. Dave, for your precious, precious time. And actually, you helped me understand a lot about nuclear fusion because I was kind of like, I kind of understood the topic in general, but you helped, get it like in depth in my mind. So thank you so much, everybody, for watching today's episode in the Advaith Vutukuru Show. Until next time, bye.